Good evening to all. This is our ninth lecture of the course, Fluid Mechanics. In the previous lecture, we have completed our discussion on the first module of the course, which was on Introduction to Fluid Mechanics and different fluid properties. Now we will be specifically talking about fluid statics in this module. So fluid statics is nothing but whenever we talk about the fluid medium at rest, then we call the branch of fluid mechanics as fluid statics. So particularly when we deal with the liquids at rest, then we call this branch as nothing but hydrostatics. And when we deal with gases at rest, then we call this as nothing but aerostatics. So this is the categorization depending upon the type of the fluid which we are using. Okay. Now, whenever we talk about the fluid statics, so the first immediate necessary condition which it has to satisfy is that shear stresses will be zero. So, and in this particular case, our one very important property comes into picture, which is nothing but pressure, and we have already seen that pressure is nothing but the normal compressive stress. So normal compressive stress is equal to stress for a fluid, and particularly whenever fluid is at rest, then major effect will be coming only from the pressure. So fundamental definition of the pressure we have already seen. It is nothing but limit delta A approaches to delta A star, where delta A star is nothing but the limit of surface area corresponding to the continuum, and this will be equal to delta F by delta A. So this is the fundamental definition of the pressure, and its unit is Pascal. And even you can write that 1 Pascal is nothing but 1 Newton per 1 unit meter square. Okay, so this is something which we have already talked about the pressure, but there are certain aspects which we need to study in more detail. For example, when we talk about the pressure, we earlier did not consider that what is the unit of whenever we are measuring its magnitude. So what is the reference state for measurement of the pressure? So that is very important. Okay, so typically when we see atmosphere is around us, and our atmospheric pressure is nothing but equal to 1 atm, or it is equal to 10 to power 5 pascals. We also call it as 1 bar, or 101.325 kilopascal. So these are the different commonly used units for pressure, and in each of the unit, what is the value of pressure that we consider, that I have written over here. Okay. Now, whenever we are measuring this pressure and we are calling it as either 1 atmospheric or 1 bar or 101.32 kilopascals, we have to specify some reference scale, that with reference to what point we are measuring it. So typically we consider, when we talk about the atmospheric pressure, on a common understanding, it can be understood like this, that atmosphere is containing the different gases, particularly air. So whatever the weight of the air molecules is at the surface where we are measuring, the atmospheric pressure, so per unit area of that surface, weight of the all air molecules per unit area is nothing but equivalent to the atmospheric pressure. Okay, so this is a common understanding to us, and we are calling this as equal to 1 bar. But when we are assigning this value as 1 bar, then what is the reference point of the scale? Like, where is 0 bar? So typically what we have a situation of absolute vacuum. So I can call a situation absolute vacuum, and absolute vacuum is the point when we are not having, no molecule is present in the system. So when there is no molecule present in system, corresponding to that, whatever the pressure I will be measuring, that pressure I will be calling as absolute zero pressure. So that pressure I will be calling as absolute zero pressure. So typically what I can do, I can represent the measurement of pressure over here in this vertical direction and say this is the bottommost reference point where value of pressure is equal to 0. So this value of pressure is corresponding to the absolute vacuum. Absolute vacuum means there is no molecule is present in the system whose pressure we are actually trying to measure. So when we have no molecule present, there will not be any molecular vibration, and corresponding to that we will be finding, we will be not be even having any weight of the molecule, so we will be finding that our value of pressure is equal to 0. However, on this scale, if I have air under the normal atmospheric pressure conditions, then I will be finding the value equal to 1 atm. So let me consider that this is I am writing in atmospheric scale. So here this value will be actually 1 atm. Okay. So this scale of measurement where we define 0 for absolute vacuum where no molecule is present, and corresponding to that we measure the pressure, that is called as nothing but the absolute scale of pressure measurement. So for example, if I take any point over here, say this is my any point where I want to measure the pressure. So with reference to absolute 0, if I measure pressure at this point, this I will be calling as nothing but my absolute pressure. Okay, because corresponding to no molecule my value is 0, and whatever the value I am now say stating at this point P, that now I am measuring with reference to the 0 absolute scale, so that is why I will be calling it as absolute pressure. Okay, and I also told you that I am having one point over here, and this point is nothing but my atmospheric pressure, and this value of atmospheric pressure is also on our absolute scale. So it means that if I write this, so my this value, this is nothing but P atmospheric, and this P atmospheric I am measuring at absolute scale. Okay, so this is one very important point. Now I may have certain value of the pressure which is not greater than the P atmosphere. It may have pressure lesser than P atmospheric conditions. So if I take a system container, and if I actually consider that gas molecules in that system are in rarefied state, okay, so it means their pressure is nothing but less than the atmospheric pressure condition, so then I may reach to some value of pressure, say P dash over here. So this particular P dash value of pressure, when I am measuring with reference to the absolute 0, it will be nothing but my P in absolute scale, P dash in absolute scale. Okay, but one important point we have to note it down over here: any pressure which is having value greater than the atmospheric pressure, so it means all the pressures over here, so these are nothing but greater than atmospheric pressure, and any value of pressure which is less than atmospheric pressure. So when P is less than P atmospheric, whatever the situation we are having, we call this as nothing but our vacuum pressure. So this is one important point to note. If my pressure is greater than atmospheric condition, then we call this as absolute pressure with reference to the absolute 0 scale. But if my pressure is less than P atmospheric conditions, then we call it as nothing but our vacuum pressure. So P dash, I can say that it is nothing but the vacuum pressure, but it is in absolute scale. Okay, so this is something which is the standard scale of pressure measurement. But apart from this absolute scale, one more important scale is also we use many times, which is called as gauge pressure. Why gauge pressure is important? Because whenever we use the different pressure measurement devices in our different fluid mechanics systems, so basically these pressure measurement devices are designed in such a way so that they give us 0 value corresponding to the local atmospheric pressure conditions. Okay, and if we measure the pressure with reference to that particular local atmospheric conditions, then whatever the value of pressure we will be having, that we call as nothing but our gauge pressure. For example, This is my initial point which I have marked over here. So if I want to measure the pressure at this point, but now I am not considering the absolute vacuum as my reference point, but I am assigning some new scale over here. I am assigning some new scale over here which gives value, zero value at this point. So this particular scale I will be calling is nothing but the gauge pressure scale. Okay, the way I have this absolute scale which defines zero pressure at absolute vacuum, this gauge pressure scale defines zero value at nothing but the 1 atmospheric pressure condition. Okay, so now if I have to measure this P value of absolute over here, so on the gauge scale, this value will be nothing but, with reference to this gauge scale, this value will be P in gauge. Okay, so and you can see over here on absolute scale this point was nothing but P atmospheric. So P atmospheric is now assigned the value 0 in the gauge scale. So if I have to make the correlation in between the absolute scale and the gauge scale, then I can simply say that my pressure in absolute scale, so you can see absolute scale is measuring from the bottom, but gauge scale is measuring from the, with reference to the atmospheric pressure condition. Okay, so it will be nothing but equal to P in the gauge scale plus P atmospheric conditions. Okay, so this relation is true for all the pressures which we are measuring above the atmospheric pressure condition. Okay, on contrary, if I have to measure a vacuum pressure means the situation of pressure less than the atmospheric pressure condition. So corresponding to that, you will be finding this is my P vacuum in absolute scale, and in gauge scale if I have to measure it, so it has to be measured with reference to this point. So with reference to this point I am moving in negative direction, so it will be having negative value. So this will be my corresponding vacuum pressure in gauge scale. Okay, so typically if you see from this, I can say that my this much magnitude up to this point whole magnitude is P atmospheric, and then this magnitude is nothing but absolute. So I can say that my P vacuum in gauge is nothing but equal to P ATM minus P vacuum in absolute. So this is the another important relation in between for conversion in between gauge and absolute scale. When we are operating in vacuum, it means our given pressure is less than the atmospheric pressure conditions. Okay, so this is one very important scale which we encounter normally in engineering practices. Okay, so if you go to your fluid mechanics lab, or if you find any other pressure measurement devices, so pressure bottle tube pressure gauges you might have seen many times. So in these pressure gauges, if you see, these are open to normal atmospheric conditions. Their needle is actually pointing towards 0. So it means they are giving the 0 reading corresponding to the local atmospheric conditions. So it means nothing but these will provide us value of pressure in gauge. Wherever so it means whenever we will be using different pressure measurement devices, mostly these devices will be providing us value in gauge scale. On contrary, when we will be using the property tables, or when we will be defining the state of a substance, so all the property tables are generally provided in absolute scale. So that is the reason we must know these correlations in between the gauge scale and the absolute scale, and depending upon our requirement we should use the appropriate scale. Okay, now apart from measurement of the pressure, its variation in different directions is also one of the important thing which is very important for actually the concepts of fluid dynamics. So now what we will do, we will consider a fluid element. So let us consider that I have a fluid element, wedge shaped fluid element, and this fluid element is making an angle theta over here, and say this is my XYZ coordinate system. So this is X, Z, and this is Y. Okay, and let us consider that normal to the plane of the board, we have width of this one. So width of this one is actually B. So B is width. It is looking like F. Let me rewrite it again. So it is nothing but small b. Okay. And delta x is this dimension and delta z is this dimension and this is theta. Let us consider that this fluid element at rest is subjected to some pressure. So of course it will be subjected to the pressure force. So force because of the pressure. So whatever the force because of the pressure it is acting. So let us consider that in this direction first it is having pressure Px, and in this direction it is subjected to pressure Pz, and normal to this interface I am writing value of pressure as Pn. Okay. Now let us consider that density of the fluid which we have considered over here is actually rho. Okay. So now for this fluid element you can see if this angle is theta, this particular angle will also be over here theta. And let us consider the length of this wedge section is nothing but delta L over here. So delta L is the length of this wedge section. Okay. So now if I have to consider the situation of fluid statics, so under the fluid statics actually this fluid element will be stationary only if the sum of the forces acting on this is equal to 0. Okay. So let's try to do that. So first we will consider that sum of all forces acting in x direction is equal to 0. So if you consider the x direction, so in x direction px amount of pressure is acting on this face, and this particular face is having height delta z and it is having width b. So if it is having width v, then force in x direction because of px pressure will become px times b into delta z. Okay. And now this is the normal. Pn is the normal to this surface, but it is making angle theta with vertical direction. So it will be having two components. So the horizontal component of the force will be nothing but it is moving in negative x direction. It is pointing in negative x direction. So we will be having minus Pn, and area of this will be delta L into B. So delta L is the length of this particular angled surface and B is its width. So I will be having B into delta L, and because we are considering the component which is parallel to x-axis, so this component is nothing but equal to sine theta from the trigonometry. Okay, so this is equal to 0. So this is my force balance in the x direction. Similarly, if I do write force balance in the z direction, so sum of all forces in z direction equal to 0. So in z direction you will be finding first a force is acting from bottom in the positive z direction. So that is nothing but Pz times delta x into B. B is the width actually, and now this pressure force is acting on this inclined surface of the fluid element. It is acting in downward direction. So minus Pn, B into delta L is area, and it is having cos component which is acting in the downward direction. Along with this, because this fluid element is present in the gravitational field, so because of the gravitational field we will be finding that weight of fluid element is also acting in the downward direction. So if you do calculate the weight of the fluid element, this will be density times volume. So volume of this wedge is delta x delta z into B divided by 2, and then we will be having G over here. So this is equal to 0. So these two equations, equation number 1 is force balance in x direction and equation number 2 is force balance in z direction. Okay. So now from equation 1, if you see delta L sine theta, so this is nothing but a right angle triangle over here. This angle is theta. So I can write that delta z will be equal to delta L sine theta and delta x will be equal to delta L cos theta. So this is coming from the trigonometry. So if I do substitute these relations, then particularly this delta L sine theta I can write as nothing but delta z, and delta L cos theta I can write as delta x in equation 1 and 2. So if I substitute this with delta z from equation 1, I will be finding that Px equal to Pn. And from the second equation, equation number 2, I will be finding that Pz minus Pn minus of 1 by 2 rho because I am dividing delta x and b, so it will be g and delta z over here. This is equal to 0. So one important thing we are getting over here, that in horizontal direction our actually force balance is same. Okay, so in horizontal direction as force balance is same, so px in horizontal direction not force balance but pressure is actually same. So because when we did the horizontal force balance, that is resulting that px equal to pn. On contrary, in vertical direction we are finding that pz minus pn is having some component of rho g into delta z also, which is coming because of the gravitational field which is acting in z direction. Okay, so now if we make one assumption that my fluid element is so small that delta z is almost approaching to 0. So if I take a very small fluid element, whose delta z is actually almost approaching to 0, then I will be finding that pz minus pn is equal to 0 and pz equal to pn. And from here one important point we are getting, that px equal to pz equal to pn. Okay, so this is one very important point. So here you can see the on this fluid element, px is the pressure acting in x direction, pz is the pressure acting in z direction, and pn is pressure acting at this inclined fluid surface. Okay, but when I said that delta z is approaching to 0, the meaning is that this plane surface will also come down and it will form nothing but a point. So my fluid element will be becoming nothing but a point. Okay, so what I can say that when my delta z is very small, it is approaching to 0, I have a wedge shaped fluid element which is acting almost like a point. Okay, now in this point you can see in x direction pressure is px, in z direction pressure is pz, and normal to the surface pressure is Pn, normal to the inclined surface. But our delta z is very small, so it means this element is acting like nothing but a point within the fluid medium. Okay, now whenever this assumption of delta z is equal to 0 is applied and our fluid element has become point, corresponding to that we are finding that pressure in x, z and n, all the directions is actually same. So this gives us very important conclusion, because the choice of the angle theta over here was arbitrary. We have not selected theta by considering a very specific direction. So because of this, theta can have any value in any direction. As theta can be oriented in any direction, the choice of theta in this particular derivation was purely arbitrary. So if we change the value of theta, then value of this Pn will keep on actually, the orientation of the Pn will keep on changing. Okay, I have drawn it wrongly. So maybe now Pn can be in this direction, then Pn can be at some other direction, it can be at other direction for different values of theta. But if we are taking the assumption that fluid element is very small and it is approaching almost a point, then for a point in a fluid medium, pressure acting from all the directions is actually same. So this is one very important conclusion for the fluid flow, which makes pressure a point function, and I can call it as a point function or a scalar, because it is having same magnitude in all the directions. Okay, so if you take this fluid element, a very small sized fluid element, so from all the directions actually pressure acting is actually same. So as the pressure acting pressure is not having any specific direction, in all the directions it is having the same value. This is the reason which makes pressure property nothing but a point function or a scalar function. Okay, now after this we will try to study one more important concept, which is called as particularly helps us to identify that why our free surfaces are always horizontal. Okay, so for that let's try to first estimate the force acting on fluid element due to pressure. So we want to estimate the force acting on fluid element due to pressure. Okay, so for this, let's consider that we have a fluid element of very small size. Okay, and it is having delta x and delta y size in x and y directions and delta z in z direction. Okay, now let's consider that in x direction we have px amount of pressure acting on this face, and on the opposite face we have px plus del p by del x into delta x pressure acting. Okay, where this del p by del x is nothing but representing the spatial rate of spatial variation in the pressure. So at one phase in x direction pressure is px, in other phase it is del p by del x, which is rate of change of pressure in the x direction multiplied with how much we have traveled in the x direction. Okay, so del p by del x is nothing but the rate of change of pressure in the x direction. So if I do so, and if I calculate that how much force is acting in x direction, particularly because of the pressure, so that will be nothing but px times the area of this element is delta y into delta z. So this is the area on which it is acting, and minus of px plus del p by del x into delta x times del y into del z. So this simplifies to minus del p by del x into delta x delta y delta z, and delta x delta y delta z is nothing but the volume of the fluid element. So I can simply write minus del p by del x into delta v, if delta v is the volume of the fluid element. Okay, so now similarly in y direction also there will be, say, pressure py over here, and on the opposite phase pressure is py plus del p by del y into delta y. Okay, so if you try to calculate the force in y direction because of the pressure, that will be coming equal to minus del p by del y into delta v. Okay, similarly in z direction I will be finding del p z because of the pressure is nothing but equal to minus del p by del z into delta v. Okay, so from here if I calculate, so these are the individual component of the pressure force because acting because of the pressure. Now if I have to calculate the total force which is acting because of the pressure, so that will become equal to, so this is a df vector, that will be becoming equal to minus of del p by del x plus del p by del y plus del p by del z into delta v. Okay, so this is the total force which is acting because of the pressure. Now what we have to do? Now if I want to calculate the force per unit volume, so say I define some pressure force F vector pressure, which is nothing but force per unit volume. So for force per unit volume it will be becoming simply equal to minus of del p by del x plus del p by del y plus del p by del z. Okay, now if I consider the del operator over here, so del operator is nothing but del by del x I cap plus del by del y j cap plus del by del z k cap. Okay, so if I apply this operator over here, and one more important thing, because when we are considering this is a force which is a vector quantity, so here I must put I cap, j cap and k cap when I have taken its summation, because this del p by del x is the force in x direction, this is the force del p by del y is the force in y direction, and this is the force in z direction. So I must put, when I am writing this vector form over here, so right hand side also should be in the vector notation. So that's why I have written the unit vectors over here. Okay, so similarly I have to put unit vectors in this equation also, which I am writing on per unit volume basis. So here I cap, j cap, k cap are nothing but the unit normal vectors in x, y and z directions. Okay, so now del by del x I cap plus del by del y del z del y j cap plus del by del z k cap. This is the definition of the del operator. So when I will be applying this del operator over the pressure field, so I can write over here that F pressure is nothing but equal to minus gradient of pressure, because pressure over here is nothing but a scalar quantity. So I have to take the gradient of this. So gradient of this is coming, actually this is nothing but a vector quantity now. Okay, so this is a mathematical term, but what does this mathematical term represents? So this we have to understand very clearly. Okay, so gradient of P, which is a vector quantity, it nothing but represents the maximum rate of change of pressure with space. Okay, so because del by del x, del by del y, del by del z, these are nothing but the spatial parameters. So as we are talking about these spatial parameters, so I have to consider over here that gradient of P is nothing but represents the maximum rate of change of pressure. Because if you can go back, so you can see that del P by del x, del P by del y, fundamentally we consider that these are nothing but the change in the pressure, rate of change of pressure in x direction, rate of change of pressure in y direction. So when we clubbed these together into a vector quantity, so this will be representing nothing but maximum rate of change of pressure with the space. Okay, and fundamentally if you see, this is a vector quantity, so this vector quantity must have a direction. Okay, so mathematically we say that gradient of P is a vector which always acts in a direction normal to constant value of P. Okay, so this, because we are talking about over here a scalar P, that's why I have written P. But if I talk about any general scalar phi, and if I am calculating the gradient of scalar phi, that will be nothing but a vector quantity, and that vector quantity has to act always normal to the plane which is having actually constant value of phi. Okay, so it means that this gradient of P vector will be acting in direction normal to constant value of P, or normal to some fixed known value of the P. Okay, so now let's try to extend this. So when we extend this for a fluid medium, so typically for a fluid medium, from Newton's law of motion, we say that sum of all forces is nothing but equal to mass into acceleration of the fluid medium. Okay, and typically for a fluid medium, we say that sum of the forces, there will be some force because of pressure. Then if fluid is moving, it is in motion, then there will be viscous forces also. So because of the shear stress, and then we will be having some body force, and body force will be depending upon the field in which our fluid element is actually subjected. For example, if it is in the presence of electric and magnetic fields, then we will be having electromagnetic forces. If it is in the gravitational field, then it will be having actually force because of the gravitational field as a body force. And then this pressure, viscous plus body force must be equal to mass into acceleration. Okay, and this is something which we see from the basic Newton's law of motion. But typically this equation we will be actually dealing in detail when we specifically talk about the fluid dynamics. Now only we are referring to the fluid statics. So for fluid statics, shear stress will be 0, that's why F viscous is 0, and fluid is not moving and it is not accelerating, so that's why its acceleration is also equal to 0. So for fluid statics, so for statics, I can simply say that force because of the pressure is equal to minus of body force. Okay, and let us consider for a normal fluid mechanics system, which we will be dealing in this particular course. So we will be having only a single external field, and that will be nothing but my gravity. Okay, so typically if I have to write on per unit volume basis, then I can write that gradient of P, okay, not gradient of P, pressure force is minus gradient of P. So minus gradient of P is force because of the pressure per unit volume. That has to be equal to minus of rho times G vector, where G vector is nothing but this is the vector for the gravitational field. Okay, so typically we see that gravitational field is can be written as dx I cap plus dy j cap plus gz k cap, and as gravity acts always in the vertical direction and that too downward direction, so I can write g vector as simply that nothing but minus gz into k cap, and these two values will be 0. Okay, similarly if I talk about the pressure, so right now whenever I have defined this fluid element, what I have considered these horizontal directions. So this is my x, this is y, and this vertical is z. So x and y, these are nothing but lying on the same horizontal plane. Okay, so their elevation is not changing, they are lying on the same horizontal plane. So as these are lying on the same horizontal plane, and just now we have seen that in normal horizontal direction for a fluid element, we have seen previously that pressure does not changes. Okay, so for gradient of P particularly, del P by del X will be 0. Similarly, del P by del Y will be 0. So we will be having only sole component responsible for variation of pressure in Z direction. So I will be having minus of del P by del Z, and that is nothing but equal to minus of rho times, and in place of G vector I can write minus Gz, because its component also only we are taking in Z direction. Okay, so from here you can see that we are getting del P by del Z is nothing but equal to minus of rho into Gz. This is one very important equation. So what does this equation shows us? This shows us that pressure varies in Z direction, and this variation of the pressure is nothing but related to the gravitational field, okay, times the density of the fluid medium. Okay, so you can see now, as I told you previously that if I have a fluid container, okay, if I have a container and in this container fluid is present, so in horizontal direction our pressure is not changing, so I can say that this particular plane is nothing but a plane of constant P value. Okay, so our gradient of P vector must be normal to this. So normal to this is nothing but the downward direction, and this is also the direction of the gravity. Okay, if I remove gravity from here, then del P by del Z will also become 0. So gravity force is acting in downward direction. So basically that is responsible for making the gradient component parallel to it. So del P by del Z to have its direction in the downward side, because of which we will be finding that the constant pressure surface must be normal to this direction of the gradient vector. So as it must be normal to this, so this has to be horizontal. So that is the reason why our free surfaces are nothing but always horizontal. So let me repeat this point again. So gravity is the field over here which is acting in downward direction, and it is responsible for the non-zero value of del P by del Z. Okay, and non-zero value of del P by del Z from gradient of P, it is clear that we have only one single value minus del P by del Z, and which is acting in the k cap direction. Okay, so it means my gradient of P vector, del P by del Z vector. So this is the gradient of P vector which is having downward direction. Okay, so as this gradient of P vector is having downward direction, from the fundamental mathematical understanding, gradient vector always acts normal to the plane of constant value of the scalar. Okay, so if it is acting in downward direction, so whatever the normal plane over here we will be getting in horizontal direction which is normal to this, that will become nothing but a plane of constant value of the pressure. Okay, so if at this entire plane value of pressure is constant, so we will be getting our free surface also at the atmospheric pressure condition, because above this we will be having atmospheric air. So everywhere over this surface our pressure will be atmospheric, which is a constant pressure. So that is the reason that we have all our free surfaces as nothing but the horizontal. Okay, so now I will stop at this point and we'll have further discussion in the next lecture.